The Moon is the Earth's closest space neighbor and its only natural satellite. It likely formed when a huge Mars-sized object crashed into our planet billions of years ago. I wasn't around then. This catastrophe turned Earth into a scorching ball of molten rock. It also pushed some material into its orbit, creating the Moon. Now, this heavily cratered sphere moves around our planet. This causes high and low tides around the globe. A bit more than 1/4 the size of Earth, it's the 5th largest natural satellite in the solar system. The Moon has several phases. For example, new, full, or crescent moon, first and last quarter. But whatever the satellite looks like, you can always find it in the night sky, and sometimes even during the day. But imagine waking up at night and noticing that the Moon looks somewhat different than usual. It seems brighter and bigger. It's hardly noticeable, especially when you're half asleep. You go back to bed, unaware that instead of the Moon, you've just seen Mercury. Close up, this planet, the nearest to the Sun, is similar to our natural satellite. Its surface is littered with craters left by space rocks. Mercury is about 2/5 the size of our planet, but it's still a bit larger than the Moon. That's why the planet would have a greater influence on Earth. Nights would become brighter, high tides would become higher, and low tides, what do you think, lower? Yup. The lunar cycle, that's the time the Moon, or rather Mercury now, needs to go through all the phases, would become 14 hours shorter. But all in all, such a replacement wouldn't have any drastic consequences for our planet. But then, how about Venus? What if, instead of the familiar satellite, we swap in the third brightest natural object after the Sun and the Moon? It's often called Earth's sister planet because their mass and size are nearly the same. Venus would be as large in our sky as Earth once appeared to the Apollo astronauts when they looked at it from the Moon's surface. The morning star would be much brighter than the Moon. For one thing, the planet reflects 6 times more sunlight. Plus, it would occupy an area at least 16 times larger. That's why nights on Earth would be as bright as early twilight now. If you looked at Venus, you'd spot vague swirling patterns in the planet's yellowish-white cloud cover. Venus wouldn't become Earth's satellite. The two planets would likely orbit around their common center of mass, and this orbit would be quite eccentric, like me. But if Venus moved with the same speed as the Moon has now, the two planets would crash into each other in the nearest future. Uh-oh. Okay, let's pull another switcheroo. If Mars was up there in the sky instead of the Moon, you'd surely notice it. The planet's disk would look reddish. Oops, sorry, make that reddish. And it would be almost twice the Moon's size. Even without a telescope, you'd be able to marvel at its unusual color and dark spots on its surface. And even if you didn't see the red planet, you'd still feel something unusual. Mars is half of Earth's size, but several times larger than the Moon. Replacing a smaller space body with a much bigger one would upset the delicate balance on our planet. If you were unlucky to be at the seaside when Mars took the Moon's place, you'd have to evacuate as soon as possible. Massive waves would rise in the oceans under Martian influence. They would crash against the shoreline like the largest tsunamis. Mars would be reflecting more sunlight than the Moon. Nights would be lighter. Terrestrial landscapes would have an eerie red tint. And you'd be able to admire the tallest mountain in the solar system, Olympus Mons, through a telescope. Mars isn't large enough to change the Earth's orbit dramatically. But with time, the two planets would probably begin to orbit each other, creating a binary planet system. And since Mars would literally be next door, voyages to this planet would become a reality. Okay, now think really big. If Jupiter replaced the Moon, Earth, as an independent planet, wouldn't exist anymore. It would instantly turn into another moon of the largest planet in the solar system. The only positive moment in this transformation? People would have an awesome sky view. Jupiter is dozens of times larger than the Moon. A gigantic, beautifully striped sphere would cover nearly all the horizon. If you had time to enjoy the show, you'd see yellow, brown, red, and white clouds floating in Jupiter's atmosphere. Sadly, the gas giant's gravitational pull would instantly cause severe earthquakes, volcanic eruptions, and tsunamis. Earth's mantle and crust would be drawn toward Jupiter, which would break the planet apart. It'd be stretched and compressed with such force that its surface would bulge back and forth by more than 300 feet. Unfortunately, Earth's speed is only 10% of the speed needed for us to stay in Jupiter's orbit. That's why our sluggish planet would crash into the gas giant in less than a day. Well, that sounds unpleasant, so let's not do that. Now, if Saturn were to replace the Moon, it would be a sight to behold. The planet is more than 35 times larger than our satellite. It means the giant golden globe would cover 18 degrees of the sky, and its rings would stretch even further, from horizon to horizon. Hey, if you like it, then you should have put a ring on it. Earth would be a bit further away from the gas giant than its own moon, Dione. And since Saturn is way more powerful than our planet, Earth would turn into its satellite, not the other way around. Unfortunately, Earth's rotational speed wouldn't be enough to keep up, and we'd most likely crash into the much larger planet within a day or two. But before burning up in Saturn's atmosphere, we'd have to pass through its magnificent rings. They're made up of pieces of comets, asteroids, and shattered moons. It wouldn't be an easy feat to get through this space debris. Plus, our planet would have to avoid Saturn's moons, all 53 of them. But what if the fall didn't happen, and Earth did turn into Saturn's 54th moon? Then the gas giant's gravitational pull would lead to massive tectonic shifts all over our globe. They would be tearing the planet's crust apart until there's nothing left. Not good either. Both Uranus and Neptune are ice giants. These planets are the same size, larger than Earth but smaller than Saturn and Jupiter. They both have icy interiors, deep atmospheres, and similar color, very beautiful bluish-green. If either of these planets replaced the Moon, the consequences would be the same. So let's flip a coin. Okay, it would be Neptune you'd see in the sky one day. Neptune is 14 times larger than the Moon. The planet would look like a bright blue hot air balloon in the sky, not only at night but during the day too. It would appear to be 15 times larger than the Sun. If everything else remained the same, a solar eclipse would seem to continue for ages. Once the Sun vanished behind Neptune's edge, our planet would be plunged into complete darkness for no less than an hour and a half. Neptune is 17 times the mass of Earth, and its gravitational pull is much stronger. That's why our planet would end up as a satellite. Yep, again. It would orbit Neptune slightly further than its own largest moon, Triton. By the way, there would be a great risk of Earth colliding with this space body. But let's assume we were lucky enough not to cross paths with Neptune satellites. Even so, there would be more than enough problems on our hands. Tides on our planet would become 1,000 times more powerful than those caused by the Moon. Neptune's gravitational force wouldn't pull Earth apart, but it would heat our planet up. The seismic activity would increase, setting off earthquakes and volcanic eruptions. Use your imagination to draw two parallel horizontal lines. Now, connect these lines at any point you want, in two different ways. With a vertical line that goes straight from the bottom line to the top one, and with a diagonal line. Which line is shorter? Of course, the vertical one. It's the shortest route to connect the top and bottom lines with each other. And that's also the most basic answer to our question. It's faster and easier to get into orbit by just going straight up from the ground. The bottom line is the Earth's surface. Our planet is a complex hodgepodge of all kinds of matter, which is combined into an impressive mass, almost 6 sextillion tons. That's like 6,000 billions of billions, lots of zeros there, just like my middle school math scores. All that math basically works like a colossal magnet that, besides other significant feats, allows the Earth to maintain one thing we all know and love – the atmosphere. The top line is the limit of the Earth's atmosphere. Anything beyond that is the planetary orbit and outer space. But the atmosphere itself is also filled with matter. It's a combination of gas that has its own density. When a shuttle is launched, all the mass of this gas was constantly pushing on it, which caused friction, effectively slowing it down. Going through a vacuum is like cutting through the air, whereas getting through the atmosphere is like going through jelly. Ooh, grape or strawberry. It took a lot of energy and force to get through it, while being pulled back by that giant gravitational magnet called Earth. Airplanes don't struggle this much with getting through the atmosphere, because they use its density to lift up from the ground and maintain altitude. Two things help them with that: the thrust of their engines and the form of their wings. The wings of an airplane force the air in front of them to split into two streams. Naturally, these streams want to reunite behind the wing, but the shape of it makes the upper stream go faster. The faster the air goes, the less dense it becomes, and that means that the airstream that goes underneath the wing is denser than the upper one. This creates a gradual lift for the airplane. Basically, wings make it so that the airplane can glide on the air. But of course, that wouldn't be possible without a huge force pushing the airplane along. This is what thrust is for. Just to take off from the ground, an airplane needs to attain a huge speed. This speed varies enormously between different kinds of airplanes: 60 miles an hour for light planes and about 150 miles per hour for airliners. And just to take off and climb to 10,000 feet, the Boeing 747 needs a little less than 3 tons of fuel. That may sound impressive, but let's look at that space shuttle. The first obvious things are the cute, tiny, stubby wings that wouldn't be of any use for a horizontal takeoff. But if one was built with more excessive wings, they wouldn't be of any use in the vacuum of space. It would also be hard to make them sturdy enough to make it through the launching process. The little wings of a space shuttle served only one purpose: to land the shuttle safely so it could be reused in future missions. They were just big enough to prevent the shuttle from spinning uncontrollably during the descent through the atmosphere and to glide it to the ground. It didn't utilize any engine operations during landing at all. The engines of the space shuttle were nothing like the engines of a plane. The airplane's engines needed air from the atmosphere to work. The shuttle's engines obviously didn't, since atmospheric air would have been hard to find in space. Instead, the shuttle used rocket engines. To show what rocket means here and how these engines work, just blow up a balloon and release it from your hand. It'll fly around until there's no air left inside, all the while being pushed in the opposite direction as the air coming out. To fly up, a rocket engine has to throw off enough thrust and burn the right amount of fuel to do the job. In fact, space shuttles needed so much fuel during their ascent to make enough thrust that they couldn't do it on its 3 engines alone. They needed 2 additional solid rocket boosters and a huge separate fuel tank that was jettisoned at the final stage of the launch. And a shuttle would only go into orbit if it had enough power. The power of a shuttle with 3 engines and 2 boosters is around 7.8 million pounds of thrust. To power up this much push, an external tank held around 1.6 million pounds of rocket fuel. And to keep the flight under control, those 3 engines had to be mind-numbingly complicated in structure. But would it be even possible to fly a shuttle into orbit if it was modified to use the atmosphere like planes? Well, unfortunately, the answer is no. It would take even more fuel to maintain the needed speed for the distance of a diagonal launching trajectory. The thing is, even if a plane climbs to the upper part of the atmosphere, the Earth still won't let it get away. To escape the atmosphere, any object that starts from the Earth would have to be fast enough to cross the point of so-called escape velocity. This velocity is needed to overpower the gravitational pull of the planet and let an object go into orbit. For our planet, this orbital speed is 17,500 miles per hour. It's obviously way faster than the speed of sound, and many times faster than the cruising speed of an airliner. Now, try to imagine an aircraft that goes this fast and how much fuel it would require. On top of that, it'd have to be sturdy enough to keep itself in one piece while doing so. The cost and complicated technology would just be unrealistic. The possibility that shuttles have become a thing of the past has caused scientists and engineers alike to try to find even better solutions for getting into orbit and beyond. One such idea proposes that in the future, people would be able to go to space on a huge space elevator. A space elevator is the concept of a huge tower that connects to a satellite at the top, which moves in line with the rotational movement of the Earth itself. The tower is supposed to be about 22,000 miles high and made of extremely durable material – carbon nanotubes. The platform inside the tower is planned to be set in motion via electromagnetic-powered vehicles. The trip from Earth to the satellite would take just 5 hours. This megastructure would allow for a cheaper and safer way of getting into space, but carbon nanotubes were proved not sturdy enough for building a tower this huge, so the search for an ideal material continues. Another project that uses a similar approach is called a space tram. The structure needed to launch this project isn't as big, but still quite impressive. It's a vertical vacuum tunnel that pushes a magnetically levitated shuttle. It won't be slowed down by the air, and it'll be pushed and accelerated with an electromagnetic force through the tunnel. It'll then shoot into the skies at a speed close to escape velocity. The shuttle powered by this tunnel will weigh less, because it won't need to carry a lot of fuel. No word yet on how human beings would survive such acceleration. Riders might look like pancakes upon arrival. If these ideas sound strange to you, and they do, then get ready for the last one. It's possible that people will use planes as a way of getting into orbit. No, I didn't lie to you previously. The plane won't go into space by itself. Instead, it'll be used as a launch platform. Even better, huh? For this purpose, a special aircraft will be made with an almost 400-foot wingspan and capable of climbing to an altitude of 35,000 feet. Small shuttles launched from this aircraft won't have to go through so much of the thick atmosphere, making it easier for them to get out from the gravitational pull of the Earth. Richard Branson is working on this technique right now with his Virgin Galactic program to take tourists to the edge of space. Why is there so much light on Earth, but almost none once you leave our planet? You might think it's light during the day and dark at night, because the Earth spins on its axis and the Sun illuminates either hemisphere. Well, that's part of the reason, but it's more complicated than that. I mean, our star shines on the Moon too, but the sky above it is always black. It comes down to the unique atmosphere surrounding our Earth. It's full of dust, dirt, gases, and water droplets, which all act like tiny mirrors and reflect the sunlight. When sunlight bumps into these small particles, it diffuses and creates different colors. That's why we see a blue sky and all those spectacular shades during sunrise and sunset. It's a whole different story elsewhere. If you find yourself on the Moon, where there's no atmosphere, the sky will be black. You'll be able to see stars even when the sun is blazing on the surface during the lunar day. The same is true of space. It's filled with lots of different gases, but it has no atmosphere with molecules to reflect sunlight. In other words, space is empty. That's why even when the sun is shining, space looks like a black void. If one day the Earth's atmosphere disappeared, it'd be just as dark as it is in space or on the Moon. That one's clear. But the sun isn't the only star or source of light in the universe. So, why don't other stars shine with blazing light at night? Well, you're not the first one to wonder about that. An astronomer named Thomas Digges researched this question back in the 16th century. Digges was sure that the universe had no end and the stars in it could not be counted. He tried to answer why all these innumerable stars don't blind us with glaring light, but failed. His questions were just way far ahead of his time, and he didn't have the tools to find the answer. In the early 19th century, German astronomer Wilhelm Obers suggested that the reason the sky is dark at night was a dusty veil that hid most of the stars from us. This idea also proved to be wrong later. The stars shed not only light, but huge energy that could heat dust particles so that they would start shining themselves. In that case, the night sky would still be light because of shining dust. And yet, the sky gets dark every evening after sunset. What's bad about this theory then? Digges, Olbers, and other astronomers of the past believed the universe was infinite, but modern astronomy knows better. The number of stars, as countless as they may seem, is simply not enough to illuminate the sky at night. The sky gets dark because the stars, just as the universe itself, don't last forever. They are finite. You see, the universe has its own borders and isn't as ancient as scientists used to think. Sure, just shy of 14 billion years is no whippersnapper to us humans, but it's still surprisingly young in cosmic terms. And it's not much for all of the light from the most distant stars to be able to reach the Earth. In other words, thanks to our fancy, powerful telescopes, we now know that it takes light billions of years to get to us from the farthest stars. This means, when we look at the sky, we glance into a very distant past. Modern telescopes can show us that the light started its journey to the Earth about 10 billion years ago. The more powerful telescopes get, the further back in time we can see. One day, we'll be able to see something that existed before stars appeared, probably by studying the dark gaps between them. But more on that here in a sec. Okay, stars don't illuminate our night sky all that much because they're really old, even as we look up at them, and they're unimaginably far away. If that's the case, then why don't less distant stars shine as bright as the sun? There should be thousands of stars much closer than those on the outskirts of the universe. Yeah, sure, there are plenty. Let's take a look at our closest space neighbor, Proxima Centauri, as an example. It's practically in our backyard, just over 4 light-years away from us. But we can't even see it in the sky without a telescope. The thing is, it's 7 times smaller than our Sun, and it gives off only a fraction of 1% of the Sun's brightness. And our close neighbor, just 4 light-years down the road, is still pretty far away, about 25 trillion miles. For comparison, our own big bright Sun is a mere 93 million miles from Earth. So our star is much bigger and closer. Other stars might be brighter than the Sun, but they're much farther from us too. But don't all those distant stars give at least some noticeable light on this planet? Well, I'll put it this way. It'd be like switching on a ton of tiny halogen light bulbs. They're not as bright as one big LED bulb, but they do give off part of its light. So, yeah, they give us a little bit of something, but it's barely noticeable. Remember, space might be empty compared to the Earth's atmosphere, but there are a lot of gases out there. They move around, form clouds, and serve as a sort of veil hiding most of the light in the Milky Way. That's why we can't see everything that's going on in our galaxy. We need special equipment for that. But it turns out Olbers was sort of right, only the curtain that covers the light is made of gas and not dust. Where the Big Bang comes into play. The theory states that the universe was born in a Big Bang 13.8 billion years ago. Since that time, everything has been moving away from the point where it all began. That is, the universe is expanding, and objects within it are getting farther from each other with time. Sources of light also move away and spread out, which means space is getting darker and the number of black areas is growing. They move at their own speed for billions of years, and our telescopes and satellites, fancy as they may be, can't notice or track this movement.